Okay, from current slide. Before we get started today, let's just go over today, okay? We will work in Chapter 3 for about an hour and a half, okay? Then we will do the first lab in Chapter 3. I think we'll get far enough in Chapter 3 that we can do the first lab. And I think you'll finish before 2 hours are over, but I'll allow you 2 hours to do the lab. That's what it's set up for. Okay, and then we'll have the first test, and you can have your formula and equation sheets. If you haven't done those yet, not a bad idea to get those together. And then we'll have the second test, the test on Chapter 2. So the first test is Chapter 1, second test is Chapter 2, because we did finish that last time. And then, in both of those, I think will take you less than 30 minutes each. So you should be able to hit the road a little earlier, and I'll feel bad about ripping you off of part of your tuition dollars, but well, y'all are kind. Y'all are just so kind. Okay. Any questions on that? So you can have a formula equation sheet for Chapter 1 and one for Chapter 2. I don't like giving two tests on the same day, but because you didn't have books, we had to postpone the other. All right. Any questions on anything from Chapter 1 or Chapter 2 you wanted to get cleared? Say when you were studying so hard the last couple of days, getting ready for the test, ran into any questions that you were burning, I'll be glad to try to clear those up.
You said you had questions for a lot of different parts?
Yeah, on the first test, yeah, the Chapter 1 test. The first one seems like there's 3 parts, the second one seems like there's 3 parts. Some of them have only 1 part, some of them may have multiple parts. I don't remember for sure. It's been a while since I actually looked at the test to remember exactly how it breaks down, but it seems like total number of blanks on the test are on the order of 17 to 20, something around there. Okay, it's a 1-page test. It's not super bad, but it does have some calculations on it. And it does have stuff for you to recall. Okay. Then the second test, I'm pretty sure has maybe 2 or 3 calculations, just sort of minor ones, pretty easy ones, I think. And then most of the rest of it is multiple choice. There may be 1 or 2 fill in the blank, but most of it's multiple choice. The first test is maybe only 1 or 2 questions that are multiple choice. The first one, the test bank, it's all multiple choice pretty much. They have some true false in it sometimes, and those are pretty, I just never liked true false questions when I was a student, and I don't like them as an instructor. So if there was a good question, I either redid it as a multiple choice or made it a fill in the blank or a short calculation or something like that. But their first test, the test bank, was just pathetic, I thought. They were nitpicking little bitty things like differences between theories and principles or something. It just was stuff that I didn't think was important, so I wouldn't think it was important for you to try to memorize or something. So I went on and I used some of their questions to come up with these questions. So I tried to stay within the content of the test bank, but I couldn't come up. Most of your tests are going to be on the order of 20 questions. So that's what I was shooting for, 20 answers. Now, they won't all be 20, but they'll be somewhere fairly close to it. All right, any other questions? All right, then Chapter 3 is dealing with energy. When you hear the word or think of the term or the concept energy, what comes to mind? What? Okay. I'm almost glad you said that, because generally, and I hear it a lot, we think of those 2 words being almost the same thing. They're really not. They're close, they're related, but they are not the same. So I'm sort of glad you said it. In fact, the lab today is going to deal with energy and power, and you'll be seeing that. So energy, one of the reasons I ask it, it's a fairly nebulous quantity, okay? Distance, displacement, time, velocity, acceleration, those are all things we sense, see, and stuff like this. Energy, though, is mostly just a concept. Okay? You can measure it, and there's certain things, but most of the time you're going to measure surrogates of it, not actually the same thing, or you're going to calculate it. Well, here's the core concept, and again, it's on the title page of your chapter, and they always put it white print on a yellow background, which makes it, you have to almost look for it to see it. Here it's a lot better. Energy is transformed through working or heating, and the total amount of energy is constant. Always. Okay? Now, you might think, well, if the total amount is constant, that's going to be really easy to deal with. No, because energy is always being transformed. Sometimes by working, sometimes by heating, sometimes by other things. The total amount remains constant, but the forms, they vary so rapidly and smoothly, it's really hard to nail them down sometimes. Okay? And I can't remember, because this is not the same picture that's in my, oh yeah, it is. This is the Glen Canyon Dam on the Colorado River between Utah and Arizona. This is before you get, let's see, on down the Colorado River. I'm trying to think which way is goodness gracious, what's the name of the really famous dam? The what? Hoover Dam, yeah. I was trying to think of the name of the president, and I knew it was that name. I don't know if it's named after him, but Hoover Dam. I think that's further down the river, because this, well, let me see again. Between Utah and Arizona, maybe, yeah, I think it's one way or another, but it's also on the Colorado River, okay? Now, what has energy got to do with the dam? Why do they have this picture in an energy chapter? Very good, okay? You can see all these towers here. This dam, in fact, most of the dams we have are hydroelectric dams. And what they're doing, and we're going to get to this later, you're backing up water on that side of the dam, right? So water's backing up there, and what that water's doing is gaining what they call potential energy, the energy of displacement or position. And then when they release it, it flows through the bottom of the dam. It's picking up large amounts of kinetic energy. Potential energy is changed to kinetic energy. Turning turbines, the kinetic energy of the turbines creates the electrical energy. And then, you have all sorts of energy transferring going on here, but the total energy remains the same, but it's changing so smoothly. It's hard to nail down exactly how much energy is where, but the total amount is the same. So here's the fundamental law. We just said it, whether you realize it or not. Conservation of energy. Energy is always conserved within a system. Okay? Now, some of the manifestations of energy are work. Work is a form of energy. Okay? Motion, the energy of motion. I just mentioned that as the water was moving through the dam. Position, I mentioned that. As the water backs up behind the dam, it's gaining the energy of position. Now, what we didn't show there, but is outside, the energy of radiation, light. Okay? It doesn't have to be light. It could be ultraviolet radiation. It could be infrared radiation. It could be cosmic radiation. It could be gamma radiation. Any of that radiation, light is one kind, is a form of energy. Heat is another. Okay? If you were to place your hand here, okay, I can feel it just slightly, but even more here. The light that's on the outside coming through the glass, the wavelength lengthens a little bit, and it changes from light energy to infrared energy, heat energy. Any of you leave your windows cracked this morning? You did? All Okay, smart move. Why? Okay. Well, why would the inside of the car get hotter than it would be outside the car? Did you leave it? Say again?
It's sealed.
Say again?
It's sealed inside, like on the heat. When the sunlight goes through there, it heats it up.
Okay. Yeah, you just described it. What you just said is what I said. When the light energy, which is the ambient temperature outside is cooler, comes into the glass, the light lengthens the wavelength, becomes infrared, which is heat energy. It gets warmer, but then the heat energy doesn't have enough energy to go back through the glass because the wavelength has gotten too long then. Okay? So it stays in, and what do we call that effect? The greenhouse effect. That's exactly what the greenhouse effect is. That's why they do greenhouses. They have a glass or plastic or what is the plastic that lets light through, those kinds of things, letting the light through, but trapping the heat inside, and therefore plants in the wintertime can have all the light they need, plus they stay warmer, and you can start plants much earlier in a greenhouse. We have a small greenhouse where we store some of our ferns and other things we want to use the next year. They freeze in the wintertime. Okay? So heat, chemical, nuclear energy. Okay? These are all manifestations of energy. I don't know why they put chemical and nuclear together. They're as separate as any of these others are. And mass itself is energy. Whoa. Can that possibly be true? What's that? Yeah, okay. You're gullible, huh? I can write anything. No. Okay. I bet you all of you know Einstein's most famous formula. What does that mean?
The energy equals mass times the speed of light.
Squared. So therefore, mass can be changed to energy. It's a lot harder to change energy to mass, but mass can be changed to energy. So mass itself is energy. You're getting into nuclear energy pretty much there. Let's just take another, don't want to take too much time on this, but the radiation energy that's coming from the sun out there right now, there's little green leaves that have come out in the last week or so. What are they doing? They may not have started yet, but I imagine they have. What's going on in those little green leaves? Second? Second? Photosynthesis. What does that mean? Photo, the prefix, what does that mean? Light. And synthesis? No, putting together something, to synthesize, okay? What it's doing is the light is hitting those leaves if they're active, and I think they are as soon as they turn green. The chlorophyll in those leaves takes that light and the wavelength of the light, that energy there, and converts it to chemical energy. Because what else the leaves are doing, they have little stomata, little holes, pores, on the underneath side and some on the top side too. And those are bringing in air. What part of the air do the leaves interested in? No. Yes, they want the carbon dioxide. And that carbon dioxide combines with water that comes up through the roots. And I know you're really interested in this, but since chemistry is part of the course, we'll do this. Let's get the pen changed. Okay. Carbon dioxide, CO2, plus water, which is H2O. That's an O, not a zero. Have y'all seen this reaction before? Yields a carbohydrate, C6H12O6. That's the simplest sugar we've got. It can be glucose, fructose, or sucrose. Okay? That's a simple sugar. Obviously, you need 6 carbons on this side to match those 6. That gets you up to 12 oxygens. Well, you have 6 oxygens. Ooh, okay, no. It's going to be a little tougher than I thought. Let's do 6 here, because 6 hydrogens to account for those. Oh yeah, that's what's happening. Forgot this. Another byproduct of that is oxygen. Okay? So you got 6 carbons here, 6 carbons there, 12 hydrogens here, 12 hydrogens there. You have 12 and 6 or 18 oxygens there. Here you have 6 from 18 would be 12, so that would be 6 oxygens there. That's it. That's a balanced chemical equation. The leaves are breathing in, so to speak, carbon dioxide. Now they're breathing in all the air. Okay? There's a very small amount of air has carbon dioxide. They take it in, they pull out the carbon dioxide, and then they synthesize with this energy of light and form a simple sugar. Well, the energy they're getting from the sun is what's binding those carbons and hydrogen and oxygens together, tearing these apart and putting those together. That's stored chemical energy in those chemical bonds. And then what happens? Those trees, let's imagine they were apple trees, they're not, or peach trees, or nut trees, or say again? Someone say something? Okay, yeah, that's what they do, and they store the sugars there in the apples, and then I just ate an apple for lunch. I had more than an apple, and I'm going to metabolize that apple, and that's going to warm my body and give me the energy to move around and do all this talking and stuff like that. So I'm converting that energy back to sound, to motion, to position, to whatever I want to do with it, okay? So that's exactly what's going on. The red light from the sun, radiations, hitting the leaves are trapping that, and that's a really complex chemical reaction that goes on. I don't know if you did this in biology or somewhere. ATP was adenosine triphosphate and adenosine biphosphate. It changes the phosphorus, stores that, and then it changes back as it makes the simple sugar. Then later, animals, bugs, us, whoever eats the product of that, and we convert it to something else. So the energy is constantly changing forms, but the total energy is the same. Okay, so those are manifestations of energy. What are some of the sources? Well, nowadays, petroleum is a big source. Thank the Middle East for most of that, but other countries have quite a bit too. We have some. Russia has some. Norway, I didn't know was a big energy producer, but I heard that on the news just this week, I think. Coal, we have lots of coal. Some problems with coal. What would be some? It's what? I still can't hear. Yeah, it pollutes. Yeah. It has a lot of ash and a lot of other things in it, like sulfurs and things like this that do some sort of bad stuff. So it's not a clean source. Petroleum is not super clean, but it's cleaner than coal. Moving water, a pretty good source. That's the dam, right? Hydroelectric. Nice source, renewable source. Nuclear, really big source, but it has some problems too. What would that be? Second? Radiation. They have to be very, very careful with constructing the plants to keep all the radiation confined, but also, unfortunately, when you're through using the nuclear fuel, it's still really seriously radioactive. So the waste product of coal you were mentioning is the dust, the ash, the sulfur, and stuff like this. the waste product from nuclear is not nearly as much, but boy, it's deadly. And right now, they store, we're going to get into this later, so I probably shouldn't spend too much time, but they store a lot of the nuclear waste, I think, inside of a mountain. I think it's either White Mountain or Green Mountain or something like that, somewhere in Utah, sort of not real close where a lot of people live, but people do live relatively close to it, and they just keep storing in some caves and stuff down inside the mountain and hope that there won't be any leakage. Well, the very best, tightest containers they can get to store it in, they don't know what it's going to be like in 100 years. Well, there'll still be a lot of radioactive waste in that container. What if that container corrodes and that leaks into the groundwater? And yeah, I mean, we could have some pretty serious things we don't even know about. Okay? Solar, another, that's what the plants have been using since they've been here, is solar energy. Okay? We are just beginning to learn to use solar energy. Any of you got a calculator? I think we mentioned this before. Yeah, some of the calculators. Is it? Yeah, I have one too, and I left it late the last time I was there. I got to pick it up next week. So it's, yeah, there are solar powered watches, calculators, all sorts of things. So yeah, those are all sources. There are others too. They didn't mention, well, yeah, these are chemical too. What are uses of this energy? Well, we use it to transport ourselves and other things. We generate electricity. We mentioned the hydroelectric, but nuclear is used for generating electricity. Coal is used for generating electricity. Nowadays, natural gas, more than petroleum, maybe not more than coal yet, but it's getting there. Okay? Yeah.
You know, you're talking about when all is bad, which of the following would be like the most useful? Not as in, like for instance, like nuclear power, it's got a lot of side effects. But what
Yeah.
are some of the cons to it?
The cons or the pros?
Yeah, the pros.
The pros. Well, just a little bit of nuclear material can provide a huge amount of energy. Okay? And it's emits no, okay, it's not fossil fuel. It's emitting no waste to the atmosphere. Huh?
Nuclear energy is
Not really. I mean, nature kind of renews it, but no, we just use it, and then we don't know what to do with the waste. But it's clean in the sense of no air pollution or water pollution or that kind of stuff. The only problem with it is the waste material and storing that safely.
Well, if the waste though has a lot of radiation, how do you know it's waste? I mean, is it what nuclear power is trying to go off of? Is the amount of stuff that it puts off?
Okay, yeah, but at some point, the stuff that's left over is unstable. That's the problem. The stuff you're using, the fuel, is relatively stable, and you control the reaction most of the time. And as long as you control that, you're producing very clean energy. Very clean energy. No air pollution, no water pollution, none of that kind of stuff. So that's the good side. But the little bit of waste that's left is very unstable stuff that you have to store and keep from contaminating other things. And the problem is it has what they call a half-life, which means it's going to hang around, and when that half-life reaches, half of it becomes stable, but still half of it hasn't. So, and the half-life is in the thousands of years. So the waste that we produce now, someone else is still going to have to be containing that waste for generations on generations on generations, and we're still doing more of it. So that's the issue, you know. What do we do with that? It would be nice if we could still use that, but it's very unstable and it's unsafe to be using than to try to create more energy or something. Yeah. Is that a little clearer? Yeah. So it adds, yeah, big benefits, much cleaner on the environment, except for the waste, you know. the waste from burning natural gas is mostly, not totally, but mostly carbon dioxide, which plants need to make more energy, but too much carbon dioxide can cause global warming, so there's always some. This is one of the moving water, that's really renewable and clean and has lots of positive things. Solar, very, very positive. So far, don't know of many negative sides on solar. It's just that it's expensive and it's not easy, okay, to do. And wind, yeah, very renewable. They didn't mention that here. Moving wind is also very useful, renewable, clean. Yeah, it has mostly positives for it. It does take up chunks of land to have enough wind turbines to run.
It'd be hard to do it here anyway.
And you just nailed it. And that's the same thing true with solar too. On average, only good for half a day. Half a day is dark. Okay, no solar there. But what's that? Right. And what they do, they store that in batteries and then so there again, the changing the forms. Okay. And yeah.
They're supposed to be cheaper than actual regular shingles. They're supposed to be strong too.
Really? Now I hadn't heard this. And this is Tesla has come out with this? Car, yeah. I've heard that guy's name. That company probably has more creativity and outside the box type thinking than most companies around. Sometimes they're way outside, but it's
using more of his own money than money that was given to him by because the oil people, coal people.
Yeah.
They don't want to see that.
They don't want to see that. You're right. Okay. So we use it for all sorts of things: heating, cooling, lighting. Manufacturing. I mean, there's just all sorts of things. And here's Terrence. If I could press the right end of the pen. All right. So this is conservation of energy and a lot more. We will go through some of this stuff again. So let's go to that first one, work. I don't know if you think of work as being energy, but that's why I ate the apple. So I could have the energy to teach the class today, right? So to speak. Work is a product of the applied force, and when they say a product, that means not a byproduct. It is literally a multiplication of the applied force and the parallel distance through which that force acts. Okay? Now I'm going to push on this chair. Okay? Now it went just a little ways there. Part of the reason for that, now I'm going to push just as much, or at least I'm going to try to. That was further. Now why? I tried not to do any bigger push. That's it exactly, okay? You see, when I do a force here, force being a vector quantity, I have one component that's down and one component that's horizontal, right? Only the component that's horizontal is doing any work on the chair, moving the chair in that direction. Parallel distance through which the force acts. So only that portion is doing any work. When I go down like this, the entire force is in that direction, so all that force. What did the other part of the force do? It pushed down on the floor, which didn't do any work for us at all. Okay? So here is the definition of work. And if you may have remembered from the last chapter, I hope you do, okay, weight is little w. And little w is, what was its formula? Yes, mass times acceleration due to gravity. So little w is equal to mg, a good formula to remember. And capital W work, one manifestation of that is force times displacement. As long as the force is in the same direction of the displacement, and displacement in the same direction of the force, whichever way you want to do it. This guy here picking up the box, What's the force there? Upward. You're having to exert a force upward, and the distance over which you lift it, that's the work you're doing. Okay? So, force in the direction of the motion times the distance that the motion moves, that is going to give you your second. Say that again.
D in the formula, is that displacement?
Yeah. Good question, actually. They're using here magnitude, so that would be distance. The magnitude of the force times the magnitude of the displacement. The reason I say that is they're written just like a multiplication. Now, if you were really doing this physics-wise, we would write it this way. And I know that's what you were after. W is equal to the vector force dotted with the displacement. Those would have been vector quantities. Okay? Now, isn't a dot the same as multiplication? In numbers, we use it that way. In physics, this means a dot product. That means a product of two vectors. FD, that means a product of two scalars. F times the magnitude of the magnitude. Not really. Vectors, remember, have this direction, not just magnitude. You can do this with magnitudes only. When you learn to multiply, you're just using numbers. You had nothing, no direction associated with it. What's that?
Kind of like speed and velocity.
You're absolutely right.
So
Speed is, yeah.
The scalar would be your speed, and velocity would be the magnitude.
Right. And here, distance is the magnitude and displacement is the vector.
So
Exactly.
How would you do that then? Like with the chair, you would push it down on it and it would move in that way. So the force would be in one direction and displacement would be in the other. How would you ever figure out what the
Okay.
Initial output.
Very good question, and y'all are going way deeper than this course requires. Here's what it is. It's magnitude of the force times magnitude of the displacement times the cosine of the angle in between. And you mentioned earlier the angle at which you pushed. So the cosine of an angle, and y'all haven't had trig, or you may have had it in high school, but the cosine of the angle is the adjacent side over the times the hypotenuse. Well, the adjacent side to this angle, there's my angle here. The adjacent side is the horizontal side, and the hypotenuse is this side. So it's only the component that's that way that's actually doing the work, and that's what the cosine does. If the cosine is very close to zero, cosine of 0 is 1. All of the force is going to that. As you increase the angle, less and less of the force until you're up here, and now the cosine of 90 is 0. I can push with more force than I did before, and it's not displacing because I'm just pressing it into the floor. No work is being done here because there's no displacement.
and where the energy goes?
What's that?
Where's the energy go?
Okay.
Using some kind of energy to it.
Okay. If you, and I can't really sense this, but I know I'm getting hot doing this, okay? I'm burning calories pushing on this, and second, it changes to thermal energy. Also, to some small extent, it's pressing against the floor, which is compressing and probably heating that up. If you had a very sensitive thermocouple down there, you could probably measure a little bit of change of temperature there too. So yeah, changing to low-level, useless thermal energy. And unfortunately, that's where most of our energy winds up. Unusable thermal waste, okay? So we'll talk about this later too, but some people say the universe is dying a heat death because it's degrading to low-level thermal that can't be used for just about anything else. Now, we're hopefully getting a little smarter with that too. Let's look at our units here. Force is measured in what? Newton. Distance or displacement is measured in meters. So here we have a Newton meter, which is by the way, a Newton is a kilogram meter per second squared. Remember, mass times acceleration, meter per second squared, times another meter, so it's a kilogram meter squared per second squared. In the SI unit, that's called the joule. Now,
It makes sense, huh?
second,
All that, and then they grab jewels, it makes sense.
it makes sense now? Or it doesn't? Okay.
So that's a joule is what you call work.
Yes.
I say that I 20 joules, that's what you call work.
That would be what you measure work in the SI system. Okay. A Newton is force. Meter is displacement. A Newton meter is a
So
joule.
that was somebody's name, and they.
That's somebody's name.
Everybody died and put their name on it.
Right.
Somebody put their name on it.
A guy named James Prescott Joule, who did a lot of the early, really technical work that related work to energy. See, for a long time they thought heat specifically was a completely separate thing. They didn't realize it was a form of energy. Okay? And James Prescott Joule did a lot of the calculations that showed what they call the mechanical equivalent of heat. And he did that. They named it Joule after him. So therefore, what symbol do we use for Joule?
J?
Yes, but what kind of J?
Okay.
Capital, because it's named after a person. They write it, his name was Joule, they write it with a small, just like they write Newton with a small. Yeah.
It's lowercase in there, that's why I said.
I know, it's lowercase here, but see, Newton is lowercase too. Seems like to me they should capitalize his name there too, but they don't. They only capitalize the unit, and here they capitalize the unit here. Now, in the U.S. customary system, we don't have a special name. Force here is measured in pounds. That's not a measure of mass, that's a measure of force, times feet, a pound-foot. Oh, what clever name could we come up with? Maybe a foot-pound? Okay, and that's exactly what we use, a foot-pound. However, I bet you, most of you, have at some time in your life used a wrench that was calibrated in foot-pounds, wasn't it? A torque wrench. Is that measuring work? No, it isn't. It's measuring torque. Now, what's the difference in those two? Yes, you've got that right. It's you got it. A torque, and usually they use a symbol called tau for torque, is equal to a vector force cross product with a displacement. It's a different kind of multiplication of vectors, and that makes torque a vector quantity. Work is a scalar quantity. A dot product produces a scalar quantity even though you're multiplying two vectors, but a cross product produces a vector quantity. Okay? No. This is beyond what the course is calling for, but y'all sort of brought it up, and it is important. And guess what? It's still measured in foot-pounds, but that's, like you said, a twisting force, which is
So it's standard, for the standard people like us, we call it foot pounds, but to other people, is it called joules? Or is it,
no, wait, okay.
or is it still
Foot-pounds of work is foot-pounds of work, and foot-pounds of torque are foot-pounds of torque, but you just have to specify.
They call it Newton meter. Just like somebody described.
Say again? Yeah,
Meter can be torque.
exactly, because if you do a dot product with the force in newtons and the displacement in that, yeah, that's the same. Here's the difference, though, okay? The force that you're exerting on a torque wrench, you do at the end of the wrench, don't you? Okay, you're pushing this way. The distance you're measuring is how far it is from what you're trying to twist to where the force is being applied. And for them to work, you need the force in the same direction. For a torque wrench to work optimally, your force and your displacement are 90 degrees from each other. That's when you get maximum torque. Okay, if you try it in the same direction, you get zero torque. How many people? Yeah. So you see they have the same units, but they're totally different quantities. But there's both forces times distances. One's a dot product and one's a cross product.
So how do you get displacement out of a car motor?
What you mean? Okay. Oh yeah. Okay. Right. Okay. I was just going to use that as an example. I bet you most of you have seen this. If someone else is inside a car gunning the engine and you're looking at that engine,
It's working.
Yes, you're torquing it. That's why they have those motor mounts that are
Yeah.
flexible and stuff. If one of those is gone, get out of the way, okay? That thing's going to come shooting out. That's where the torque is in the engine. What you're doing is controlling that and moving all that energy to the differential, to the wheels and stuff like that. Otherwise, that thing would be flying out of the hood of the car. Okay, that's torque. Okay, not here. We're dealing with work here. Boy, y'all are on top of it.
I got a question.
Yes.
You go back, in basically the whole chapter we've been going over is SI.
Right.
And we got foot pounds on board. They still do that?
Yeah, you're allowed to. Yeah.
All new meters.
Yeah, I mean, here in the U.S., we use them both. We actually use U.S. customary more. It's you guys working on cars because you have to sell those internationally. You've had to convert to SI and using metric and stuff like that.
Everybody around the world, they measure.
No, most of the people use SI units. The U.S. and a few countries that do most of their trade with the U.S. are the only people on the planet that still use U.S. customary. It used to be called the British system. Say again? Metric, because
If you look in the specs, they still use foot pounds.
yeah.
In the top part.
Right. Well, because the people who are going to be reading those specs don't know what the metric things are. They have to use the units because they want to have an international market. And if they use nuts and bolts in 3/4 and 5/8 and things like this, no one would buy it because they don't have those tools. What's that? It really is big time. That's why the rest of the world's going to it. It's so uniform. And why in the world we are is just because we are inertia. You know, we don't want to change direction. We've always done it this way. What's that? Yeah. Yeah, right. A lot of. Okay. Was that all you had on this slide? You said go back. Yeah. What's that now?
I just asked for distance of displacement in the formula,
See, you shouldn't ask such difficult questions. Okay. So the units of work, we just talked about them. And energy, by the way, is a joule. Capital J, named after James Prescott Joule. However, if you go no distance, you're not doing any work.
Well, if you're pushing down, you're not moving.
What's that?
If you're pushing down on something, it's not moving.
And not moving, you're doing zero work. Okay.
You get tired.
Yeah, you're expending energy, but you're not doing work. Now, all energy expended goes to work, and not all work is a transfer of energy. Okay. Here's a dumb example I give. When we bought the house that we currently live in now, we've been living over on one side of south side Birmingham, and we liked it there. It was great, nice. But we were in a small 2-bedroom, 1-bath house. It was just the two of us. But when we had family come, it was pretty crowded. Okay, so and family was using us as stop-off place more and more, and we liked having them. But we really need, and them too. My wife liked to buy furniture, and soon the house was too full of furniture. So anyway, we wanted to get a bigger place so we could have, more flexibility. So we bought this place over in Forest Park, which is the other side of south side Birmingham. And there we had trees in the yard. We didn't have any trees except the ones we planted in our yard before. And it was moved out of a 1920s house. Fortunately, my wife likes old things. Okay. Not that funny. Okay. And we moved into a much newer house, a 1930s house. Okay. But the original house had been built on a nice plot. It was a hill. It was a hilly area. A lot of Birmingham is. But they had leveled off this place and built the house. But then some later owner had decided they wanted to expand. They wanted to add a den and a porch on the back, but they had to dig into the hillside to do so. Okay, because it was coming down in the backyard, going down in the front, Well, they had to dig into this. Well, when I was looking at it, number one, it made the house look a little squatty in the back because the soil came almost up to the windows, and they were short windows, I wasn't concerned as much with the looks, but I said to Karen, we've got all that hydraulic pressure coming down from the yard in the back. They don't have anywhere for the water to run off. It's all going against the side of the house. Now, it's fairly recent construction within the last 10 or 15 years, so it's probably okay now, but in time, that just adding more and more pressure there. So I said, we really need to do something about diverting the water. So maybe terrace, doing something to get the water so it doesn't run against the house. And I said the other thing is they had the soil right up against the windows, okay? And it looked like to me, and not just the windows, the screen porch they had on the porch over here, right up to I said there's wood to ground contact. Now I'm sure they use treated lumber, but it's not going to last because the treatment in that, the poison they do in that to keep the bugs from eating, it leaches out over time. So we're going to have a problem with termites if we don't get the soil away from the wood. They call that soil to ground contact. Okay? You don't want that. So Karen said, good, I wanted a patio anyway. Way bigger job than I had in mind, okay? And fortunately that summer, it was the first summer after I started working here. We were Veteran State Technical School then. And one of the reasons I was hired was to teach the automotive math classes. Now back then, they had their own math class. We were a technical college, so we had the automotive math class. It was called Vocational Technical Math. And we had a book that was geared just for automotive students, So I was teaching. Say again? Well, we were on quarters then, not semesters. And in quarters, you had a 10-week quarter. What the students did then, they were in class 5 weeks, and at the dealership, they were co-oping in a quarter, not in a semester. But we had 4 quarters in the year, so they did it summer too, okay? And I've been teaching that, and also physics, not just to them, but for the electronics people and the drafting design people, they took physics too. So anyway, that's what I was hired to do. Well, that summer, enrollment was down. We still had the automotive students because they were here, so I had 2 5-week terms of them in the summer, but nothing else. I was a new kid on the block, so full-time instructors had been here longer. They got the load, and I only had that. So I taught the first 5 weeks, had the second 5 weeks free, and even the first 5 weeks was part-time, so I just came in and taught. So that summer, after we bought the house in October, that next summer, I started digging the patio, okay? And in digging the patio, which is a lot bigger job than what I had in mind, you dig very far in Birmingham, you're going to hit rock, okay? And boy, did I come in. I came into many of them, but usually after half hour, 45 minutes of digging around, I got it loose enough that I could get it out. I had this one sitting right in the middle of where our patio was, but it was completely underground when I started, but I hit it, and it was huge. It was a boulder, okay? Big old boulder there, and I thought, how deep is this thing going to go? And I worked literally for days trying to get that thing to move. Now, I use the term I worked, but guess what? I had cheater bars, picks, I had everything I could think of. No, just to put patio in, And it was, yeah, just ground level, yeah. And it was right in the middle of it, pretty close to the middle of it. And no matter what I did, how much I grunted and sweated and did all that, was I doing work on the rock? Okay, no, because it wasn't moving. So if there is no displacement, there is no work. I did not want to hear that. Okay, I mean, I felt like I was working, but as long. Now, when I was moving soil, yeah, that was doing work. When I was trying to move that rock, I could Finally, I got it to the place. Pick, shovel, and wheelbarrow. Okay. And I had a sledgehammer. It wasn't making a dent in it. Yeah. Now I didn't have a jackhammer. Say again? Okay. Well, the thing is, like I said, we had lots of trees in the yard. I would have had a bobcat in there, but there was no room to work. Okay. Okay. So I was digging it out to get there. I'll tell you this part later, but halfway through, I ran out of summer, and the 5 weeks were over, and we were starting back full time. We hired over Labor Day weekend a bobcat to come in, because by that time I had a big enough space for him to get in, and he could get in, and he's the one that finally, in his shovel, picked up the rock and hauled it off. So it was huge though. So my point though, if I wasn't moving it, I was doing no work. Okay? Now, displacement perpendicular to the applied force is also no work. Okay? Now, you might say, what in the world are you talking about there? Remember our story of the planets going around the sun, the moon going around the earth? The force is this way, but the motion is that way. Very close to perpendicular. The sun is not doing any work on the earth to speak of, and neither is the earth doing work on the moon, which is sort of a good thing, because if we were, we'd be spiraling in. The moon would be spiraling into us, and we'd be spiraling into the sun. So that force times that perpendicular, work-wise, no work. Okay? So even though there is displacement, it's not, work is not involved with it. All right. Here's another sort of a, compared to what we've been doing, a nebulous picture here. Here we have a book on the third, next to the bottom shelf, and we take it off here and move it up here. Have we done work? Sure. We had to exert the force equal to the weight of the book. Weight of the book would be mass times acceleration due to gravity, mg. That's the force that you have to do to lift the book, and the distance that you lift it, whatever that distance is, force times distance there in the same direction. That's the work you did on the book. Okay? If you took the book and slid it down this way, gravity is this way, you're really doing no work against gravity, you're really not doing much work. Okay, yeah, if you're pushing it down, but if you lift it ever so slightly, you do that much work, okay, and move it down here. But if there's no friction, no work. But you're right, if you slid it down there, there would be a little bit of friction, okay? Because you have to do work against the friction. Very good. That's beyond where we are here, but we're going to get there later. Okay. I think this is the place where we do example 3.1. How much work is needed to lift a 5-kilogram backpack? What's that a measure of? Mass. This is mass of the backpack. Okay. To a shelf 1 meter above the floor. 1.0 meters. What's that? That's your distance that you're lifting it. Okay, very good. So how much work is needed to lift that 5-kilogram backpack to a shelf 1 meter above the floor? So we're looking for work. Capital W. How much work? Yes, you do. Excellent. You can't use mass. You have to use force, which is a weight. So what is the weight of that backpack? 5.0 kilograms. That's the mass. Oops. Times the acceleration due to gravity, which is? Say again? 9.8 meters per second squared. It used to be, but they changed it last year. No, I'm just kidding. Okay. All right. So you first got it, and this weight is the force, okay? And that will be what? Anyone do it quickly? Something like 49? Oh, you're getting your calculator? Okay. I thought I didn't. Second? 49 what? Kilogram, meter per second squared. Another name for that? A Newton. That could also be called a Newton, capital N Newton. Okay, now we're ready to calculate work. And what is work? Yeah, force times the distance. And the force here is the weight. 49, we can call it newtons, times the distance. 1 meter, 1.0 meter. That's going to be 49 Newton meters, which is also joules. Okay. Now, 49 is 49, isn't it? No, it isn't, because a Newton is a vector quantity with a direction. Work is a scalar quantity. It doesn't have any. That's one thing, but there are different measurements too. Just happen to be you're just multiplying by 1 meter. Anything less than 1 or greater than 1 is going to change that 49 ever so slightly. Okay. Does that make sense? Well, if you're lifting it, generally that's up. That's what. Okay, you could be, but it says by the connotation is lift the thing above, so many meters above the floor. So, okay, if the context gives it away, it's okay. But if it doesn't, like in the last lab when we were talking about this, y'all drew arrows on your lab, when the balls were rolling too, because momentum was a vector quantity. And to calculate the momentum, you had to take the direction into account. Same thing here too. Now, your question is, what if the force was like this? The question said how far it lifted over the floor. So you're still talking the perpendicular distance. Even though you lifted this way, only the component in the direction of the displacement is what you use.
We don't have to write anything.
That's all you have to say, unless you need it for clarity. Like if this was up or down, you might need to say that. This is pretty obvious as up. Okay? Now, let's do example 3.2. I can go on and clear this because it has nothing to do with that problem. How much work is required to lift a 50-pound box? Okay, what is that a measure of? That's a weight already, which is a force. A weight is a force, okay? So that's a weight or a force. Vertically, so they're giving you the direction there, a distance of 2 feet. What's 2 feet a measure of? That's your distance, okay? Yeah, and what would that be? The work is equal to force times displacement, okay? And that would be 100 what? Foot-pounds. Very good. Foot-pounds. That's what we measure work in the U.S. customary system. 100 foot-pounds. Now, there is a very good little blurb at the top of page 64 and 65 in my book. I don't know what it is in yours. It's sort of in a bluish lavender sort of color there. It's called Simple Machines. This is one of the few times they have the blurb as a slide as well. And you have used these. I know you have. I'd say every one of you has, okay? The basic premise in these simple machines is work in equals work out, okay? But because energy or work is conserved. Are forces conserved? No, okay? Can you lift a car?
If you get mad enough, probably you could.
Say again?
If you get mad enough, you probably could.
With an even temper, can you lift a car? With an even temper. You don't have to get mad, okay? No, it doesn't. Huh? No, I wouldn't say even that. I bet you've done it. Have you ever had a flat tire? With a jack, exactly. You have lifted a car, haven't you?
I mean,
Yes, you have.
I knew a guy
What's that?
So I knew a guy that could pick up the front end of a one-ton pickup all by himself.
I wouldn't want to mess with him.
Grab
Okay.
the bumper.
Yeah.
Pick it up.
Okay. I'm not going to mess with that guy. Okay.
Well, you can't change the plate.
But you
No,
see,
you got a 6
with a
barrel.
mechanical jack, you can lift the
Oh,
car.
yeah, you can.
Of course you can.
Mechanical hydraulic.
Huh? No, okay, now you don't even need. Okay, with a hydraulic jack, not one that's powered somewhere else, that you do this, it's even better. Okay? Because there's less friction in that. Okay? The old hand jack, you're losing a lot, but a hydraulic's even better. Even with one, I'm not talking about you press a button and it does, Yeah. And the screw jack, yeah. You have lifted cars before. Why? Because the work in equals work out. The force is very different. The force you're putting on that jack, I'm betting, is less than 100 pounds. Okay? And you're lifting a 2,000-pound car, maybe. Not even a smart car.
You know the old jacks you used to put on the bumper?
Yeah.
You were actually raising the car, then click, you raise it again.
Exactly.
And as you got it higher, you had to use more.
Okay? Yeah, and here's what it was. Your arm was doing like this, okay? A distance, and how much was the click? An inch or so. So you're doing maybe 18 inches here for half an inch there. You know what you call that? The mechanical advantage, 36-1. If it was 18 inches for half an inch, you have a 31. Because then you were able with 1 pound of force, 100 pounds of force here, you were then able, 36 times that, 3,600 pounds up. So your force is multiplied by the ratio of the distance. Yes, as the distance goes up, the forces that you have to exert goes down, or if the distance, you're doing this much to that much, the force goes up. Yeah, exactly. By that same ratio. Now, believe it or not, an inclined plane, and you were almost describing this before, your force is in this direction, but you're lifting in this direction. You're exerting a force this way, and it can be a significant force. You're only lifting maybe, that depends on how the slope of that plane, but with a little force, if that plane is at a low enough angle, you can pull a pretty heavy thing up there, because you're an inclined plane, you're exerting a force over that much distance to lift it maybe that much. So an inclined plane is an example of a simple machine. A wedge is the same type thing. Have any of you ever taken a piece of big old log of oak wood and with your fingers pull that thing apart? No. Huh? You use a wedge.
There's like that much at the end of it.
Yeah. You can't do that. Yeah, okay. We're not doing hydraulics here. But if you take a wedge and you can hit with the same force that you would have been pulling with, but hit on that wedge, then you're not going, that force is acting over a big long distance. If you swing that hammer like the sledgehammer like that, but the wedge is moving just a little bit, so you can, the distance times force equal distance times force. Work in equal work out. I hate to ask this question, but I will. What's a screw? Okay, get it. Okay. What is a screw? It's an inclined plane wrapped around the axle. Isn't it? That's exactly it. And that's why screws are so much stronger at holding things together than nails are. Nails is just friction. A screw actually has, and as you screw something together, you're moving a very little distance, but you can have a huge amount of force on it. A lever. I think that's where the picture comes in. Oh, this is basic principle, work in equal work out. Okay? Work in is force in times distance in. Work out is force out times distance out. Generally, the force in, the input, is a small force 1 over a large distance. The output is a large force moving a large weight a very small distance. But that's what you're doing. Your conservation of energy, not conservation of force, not conservation of distance, but conservation of work or energy. What's that? That's it. Leverage. That's exactly it. That's where a lever comes in. That's where the word comes from. So what they've done here is divide, distance in divided over on both sides. So now you have distance out over distance in. That's your force multiplier. No, I think they did it this way. Distance out divided into distance in. That's your force multiplier. Whatever that comes up. This is a big number. That's a small number. The mechanical advantage, that's what it gives you, a big number. And that multiplies your force and gives you a big force out. They've switched sides on it and stuff, but that's what they've done here. Divided by distance out, switch sides, and your force out is this. They call it the mechanical advantage, the force multiplier, distance in over distance out, that ratio times the force in. And so a small force in with a large ratio gives you a big force out, lifting a car. All right, here's this scrawny little gal here. Look how thin her arms are there. She's trying to lift 300 pounds. You think she can? Sure, she's using a lever in this case. What the lever is, it has a fulcrum somewhere. Say it again? Oh, is it? Okay, the new book changed it too.
Yeah, that's more American right there.
Yeah, my book has it too. The old slide had it in U.S. customary. This has it in the books that now have it. So just change this to newtons here, meters here, newton here, meter there. It's the same. No, they actually use smaller numbers too.
Well, they use the same number.
No, well, not for the distance. Yeah, they use the same number for the forces, but it's in so doing, I think they screwed it up. Okay, that would be 60 Newton meters, which would be 60 joules, and here 0.2 times 300, that gives you 100. No, they kind of mess that up. Okay. Yeah, no, that's right. 0.2 times 3, yeah. That would be 60. You're right. They got it right. 0.2 meters times 300 newtons would be 60 newtons. And then 60 joules, so 60 newtons times 1 meter would be 60 joules. So yeah, they got the numbers right. Now, how does she do this? By pulling the fulcrum here. She put the fulcrum over here. Yeah, she's not going to do it. Put the fulcrum close enough. I did that with that rock. I mean, I got another rock as far close to that as I could, to have something under the rock there, and I could not move that thing. I mean, I was standing on my cheater bar, and it just wasn't working at all. Okay, because it's way too big a mass or force. All right, so that's what a lever is. Wheel and axle, simple machine too. Your axle's turning like this, your wheel is turning like this. The outer rim of the wheel turns compared to this. Small force here, big force here, smaller force here, but bigger distance, okay? Pulleys do the same thing. Now, there's two types of pulleys. One merely changes direction. If I have a single pulley up here, and I go to lift Charles, I'm going to have to really work to get him up. But if I go up, down, and up again, okay, I can do it with half his weight. My force here would be half. Because guess what? The pulley down here, for every foot, say, of rope that I pull here, half a foot here, half a foot there, so I'm only lifting half the distance. So I can do twice by, say, a force of Exactly. Yeah. How many loops around the bottom? That's all. Loops around the top don't do anything to change direction, which is nice to have, but it doesn't give you any mechanical advantage. It's what's on the bottom. Okay, which relates to how many loops you have. Okay. What's that?
That's an employment question.
Oh, really? Oh, nice. All right. That was it. The one in the book goes a little bit further. It shows 3 types of levers. This is one here is what they call a type, they don't even, it's a first class lever. Your force is down here and your resistance is up there, okay? Effort and resistance, I guess, is what they do, okay? First class lever. It changes direction, and depending on where you put the fulcrum, if your fulcrum is closer here, then you have greater mechanical advantage. Closer here, you have less effect. All right, we know that one. In your book, the second class lever has the effort at this end, the fulcrum at that end, and the resistance or the load in the middle. What kind of lever? What is an example of that one? Now, I bet you most of you have used one of these before, too. A wheelbarrow, okay? A wheelbarrow is a second class lever. You can lift basically twice the force you pick up, you can have twice that weight in there, and you can still get it to work. Of course, you have the advantage of the wheel in front, too. But the third class lever, resistance at that end, the effort at this end, and the fulcrum at this end. What in the world could that be? Say again? Scale? It could be. I think I know what you're talking about. Did you ever pick cotton? the cotton scales they had in the field, I had to do a little bit of that when I was young. The cotton scales they used in the field had one of those kind on it, and that's why when you said that, that's exactly what came to mind. I never could pick my much cotton, you know. I did not want to do it, but okay.
I did it on paywall. They
Yeah,
didn't pay us.
right. It is miserable work, okay? But here, let me point it out. The load's down there, your effort's here, and the fulcrum's here. A shovel. I also think of a pitchfork. The idea there, you're not lifting that much, but you're going a long distance with it. So what you're doing, that's in reverse. Your mechanical advantage the other way. The load's going the long distance, and you're not having to go as far. I was thinking pitching hay, you know, with a pitchfork. Same type deal. Okay, enough of that.
Cantilever.
About what?
Cantilever.
Cantilever. I've heard the term, but I can't picture what it is now.
Out here.
Right.
And it's got so much weight back here.
Right.
This.
Got it. Okay. I believe that's more like a first class. I'm not absolutely certain, but I believe it is. That would be something like what you would use. Yeah, okay. Yeah, so that's probably more like your third class. You're probably right. Okay, you're right. That's more like the third class. You can get more distance out of it. Got it. All right, now we're moving to power. And earlier you had said power was work, right? Not quite. Related, but not the same. Power is the rate at which work is done, or the rate at which energy is transformed. So remember when we started with distance or displacement? What's the next thing we did to it? You did it in lab, the second lab. Divided by the time. And what quantity did you get then? Distance divided by time gave you? Speed or velocity, exactly. Okay? Then when you had a velocity, what do we do with it? Divided by time and got acceleration, exactly. It seems like we just about everything we run into. Well, let's see what happens if we take the time rate of that, Time rate of distance is velocity, time rate of this. So yeah, that's why the clock is here. That's 1 horsepower, you got it, okay? The force, 550 pounds, acting over 1 foot for 1 second, that gives you 1 horsepower. See, time is involved with power. Time is not involved with work. Okay? Now, let's go back to my digging in the backyard, our patio. Like I said, for about 5 weeks, for most of the day during those 5 weeks, we had a few rainy days, not nearly enough if I remember right, but a few rainy days. But other than that, 5 days a week, even 6 days a week, we were doing it on Saturday. Maybe a little on Sunday, but not too much. I needed 1 day off. So mostly 6 days a week, pick, shovel, and wheelbarrow. Now, I also was moving the soil a long distance too, and that took time because what we did, you won't need to know all that, but I was building terraces in the yard. So I was using the soil we dug out of here to build terraces in the yard, and then we planted azaleas on those and got a fairly nice looking yard until the drought last summer. So you're going to have to replace a lot of those. But that's beside the point. So for 5 weeks, with a pick, shovel, and wheelbarrow, I was moving that soil. 5 weeks ran out, time to start back. Labor Day came. We called around. We got a guy, and I had finally enough of an area back there that you could get a bobcat in without killing trees or hitting the house or something. So it was safe for him to do. He brought the bobcat in, and in basically a little over half a day's work, he moved as much soil as I had done in 5 weeks. What was the difference? Who did more work? No, we did the same amount of work. I said he moved the same amount of soil as I had done in 5 weeks. He had a shorter time, so therefore, no, he did the same amount of work. He had more power. I guarantee you, at my best, I was probably less than 1/3 of a horsepower. And that bobcat, I'm sure, was way over 250 horsepower, okay? At least I want to think that anyway. So, yeah, he had a lot more power than me. We did the same work. I did it in a long time. He did it in a short time. I had not much power. He had a lot. So what is power? Work divided by time. The rate at which you're doing work. Time rate of change. Okay? So power is work divided by time. Now, let's go SI units. What was our work in SI units? Joule. Time? Second. A joule per second is yeah, but what's the unit? No, that's U.S. customary. Joule per second. You ought to know. Have you taken any electronics? I knew you had. What do you measure power with there? Watts. What? What? Never mind. Okay. So power is measured in watt. No, yeah, okay. Yeah, electrical power is also measured in watt. That's the beauty of the metric system, the SI system. Yeah, you measure any kind of power using the same units. Watts, kilowatts, milliwatts, whatever. Gigawatts. Okay. So, now don't get this crossed up. Power is measured in watts, and what symbol do you think we use for that? Letter. Yeah. No, large W. Why? Named after James Watts, he's the one that came up with horsepower, by the way. Huh? W. Capital W is Watt. No? Okay. Now that's what I was going to say. These are your parameters. These are the symbols that represent the quantities. Watt is the unit that measures the quantity. So 7 watts, that would be a measure of power. Power is given the symbol P. Okay?
I imagine all these guys living at the same time. It's just a big argument. I want my calculator.
Well,
yours don't need to be calculated. I gave you your information.
No. Now, actually, all the things named after people were given capital letters.
So,
Time wasn't named after any. Second wasn't named after anyone, so it wasn't. Now, the reason W is capitalized is because we'd already used little w for weight, so we needed work to be capital W. That's not a unit. That's the parameter that represents work. Okay. So, strange but true.
So like in electrical, I said that volts times amps is
Yeah, you're right, and we'll talk about that in a couple
Like
chapters.
How much work it is, and amps would be like how fast.
Okay.
Yeah, volts is force.
Okay.
Electrical-
All right. It has to do with force. Since you ask it, I'll answer.
Kind of good.
A volt is a no. It's work per unit per joule. Oh, I mean work per coulomb. Work per charge. Joule per coulomb. Okay. And amperes is the flow of charge, which is coulomb per second. So you multiply joules per coulomb, work, energy per unit of charge, times coulombs per second. The coulombs cancel out, you get joules per second. Watt. Exactly the same. Okay, energy per time. Now, how about U.S. customary? What would be power measured in there? What is work measured in? Foot pounds per second. Foot pounds per second. Unless you divide that by 550 foot-pounds per second, which is 1 horsepower, then you get horsepower. That's what we'll do in lab. We will actually use the U.S. customary units for once. Okay. What's that? Okay. Where they got that from, what James Watt said, what can an average dray horse, which is a working horse, what can he average over a day's labor? About 550 pounds. Certainly he can do more than that, but to do it continuously for several hours a day, around 550 pounds. That many. That's how he came up with it. I don't know how he did, but that's what I've always heard. Okay? All right. There's a little concept supplied here. Book work. In other words, how much work does it take to lift a book? Now, these bigger books, not your little one, but the bigger ones are probably getting close to a kilogram. Probably not quite, but pretty close to a kilogram. Okay? And then if you lift it 1 meter, which would be, what, about there, you could calculate how much work you had done. Now, power is the rate at which work is done, work per unit time. The units are watts for the SI unit. Horsepower is one of the ones for U.S. customary. Now, a watt's a pretty small amount of energy, okay? Of power, because a joule is a pretty small amount of energy, okay? So quite often electrically, what do we use to measure power? Not watts, but kilowatts, 1,000 watts, okay? Don't you usually say kilowatt rather than watts? You can do watts, but they would be huge numbers, okay? So let's talk about walking versus running up the stairs. And guess what? This is today's lab. This is it.
We don't run upstairs.
Yeah, I'm going to run you till your tongues hang out. No. Okay. All right.
Well, if I start my tongue hanging out.
That what?
Well, if I start my tongue hanging out.
Oh, that'll be normal. What? No, never mind. Okay. All right. All right. Here's this old guy barely getting up the stairs. How much work is he doing?
I don't think we're going to be right for this lab here.
What's that?
I don't think we're going to be right for this lab. It's supposed to be over there.
Okay, you may not be this slow. Okay, I got it. Well, Camp may be. I mean, it's tongue hanging out. Huh?
We don't watch you run?
Oh, no. I'm going to watch you run. Okay. Okay. I've already done the lab. Okay. How much work's he doing? Okay, you're absolutely right. If he goes from here to there, he's done the same amount of work as that one. This one goes to it much faster, shorter time, so who has more power? The guy on the bottom. You're absolutely right. The work he's doing, does it make any difference the slant of the stairs? No, he's doing work against gravity. It's how far he has lifted himself from here to here. That's the amount of work he did. Not the distance this way, not the distance this way, only the vertical distance, because he's doing work against gravity.
What about that? A young man wouldn't work.
Say again?
A young man wouldn't do as much work as an old person.
You're saying we old people are fat. Is that what you're saying? I think I get what you're drifting at, yeah.
Slower, you're doing more work, right?
No. If the same weight is moving the same distance, and this mg is the same, it's actually the same guy. He took his Geritol. No, y'all don't remember Geritol. Okay. If it was the same, and y'all are actually going to be doing this too. You're going to walk them and you're going to run them. Now, what was the comment? I need to get that. Okay. Yeah.
You said Geritol, is that like cocaine?
What do you know about cocaine? Never. Don't answer that question. Okay.
Hey, we're recording this.
Let's go back to
In the back when you remember Geritol? They don't know. That used to be sort of an iron supplement. They told old people if they took it, they'd have more energy. It was snake oil, I think, but I don't know. No. Huh? What'd you say? And that was a different kind of energy. Never mind. We won't go there either. Okay. Okay. Never mind. This is going downhill fast. He's heading the wrong direction here. Okay, we're going up the stairs here. Okay. The work done, force is mg, right? Weight is mg. Height is the displacement. mgh is the work done. Okay? Mass times acceleration due to gravity, that's weight, which is force, times distance, that's work. That's the work. Okay? And the time it took him an awful long time to get up there, took him a lot less time. The work is the same, the power, weight difference. Long time period here, small power, short time period here, high power. Okay. Now, that's what the example's going to be. That's what your lab's going to be. Now, any of you have your own place? Once a month, you have to pay the rent. Yeah, but okay. Guess what? It's not. Hey, you got it. It's not a power bill. It's an energy bill. You don't pay for the power, you pay for the energy. Have you ever noticed the unit that you're paying for? Units are important. Kilowatt hour. Now, where does that come from? We just said kilowatt is a measure of power, but then you multiply that by hour, and what is hour a measure of? Time. And what was power but energy over time, or work over time? Multiply both sides by time, and you get energy. You're paying for energy because you're paying in kilowatt hours. That's what you're purchasing. The power is not what you're buying. Even we call it the power bill, Alabama Power Company, and that kind of stuff. Actually, thinking back on it, when I was young, I can remember my grandmother always called it the light bill. Why would she call it that? Because back when they first got it, all they used it for was light. They wanted to get away from kerosene lanterns and that kind of stuff. They had electricity run to the houses. They still had the wood stove. They still had the boiler under the house, or the natural gas or propane or whatever it was to do the heating or use fireplaces. All they used the electricity for was the light. So to her, even after she used it for a dryer and everything else, it's still the light bill, because originally that's what it was. They used it for. Okay, that's neither here nor there. All right, let's do example 3.3. let's see what that will be. Okay, we'll do it here. And I will erase this stuff. Okay. An electric lift can raise a 500 kilogram, what's that a measure of? Mass, not weight, okay. A distance of, oops, I gave it away, 10 meters. That's going to be your distance, very good. In 5.0 seconds. That's your time, okay. What is the power of the lift? We're looking for power. What in the world is that power? Say again? Yeah, you got to first get your weight. Your weight. Little w is mg, so that's going to be, say again? 4,900, not pounds. Kilogram, meter per second squared. Newton, okay. Got that? That's the weight or force. That's Newton. What else we need? Okay, you got to divide by time at some point. That's your 5.0 seconds. But Newton's force per second, I don't know what that is. What else we need there? The what? No, that's already in the Newton. That was here. This is kilogram meter per second squared. That's already in the Newton, huh? Yeah, the distance. We got to have the distance. Force times distance is work. So that's times 10.0 meters, right? Yeah. And that would be, I'm going to do this, say again? No, you got to have, power is work divided by time. Power is work or energy divided by time. So you have to have, this was force. You have to multiply that by distance to get work. Now I'm going to do it a little bit easier. I'm going 5 into 10. That will be 2, then double that, and that gives me 9,800 watt. Watt. And what's a Newton meter per second? A watt. No, Newton meter is a joule. Watt, yeah, that's why I kept saying a watt. A watt. A watt. Okay. A what? Okay. Okay, exactly. That was going to be my next question. If I wanted a smaller number but a bigger unit, that would be 9.8 kilowatts. Very good. Now that's actually, no, I think it's 2 digits. It should be. 9.8 kilowatts. But what if we were stuck in the mud, U.S. customary system? We need, and we want to know, what is that power in horsepower? Now, we haven't mentioned those. Let's back up a little bit, and we'll see some conversions here. Okay? I'm trying to find them. Okay, here it goes. Okay. Here's some conversions for you. First, you should know this one. 550 foot-pounds, that's work, per second, that's 1 horsepower. That's U.S. customary only. Okay? But then to go back and forth between the two, remember I said a watt is a small amount of power. It takes 746 watts to make 1 horsepower. So a watt is small, horsepower is pretty big. 746 watt is 1 horsepower. Okay? Okay, yeah, take that 9,800, you're absolutely right. I would say multiply it by blank blank, and you're trying to get the horsepower, right? So what goes where? Say again? Okay, yeah, but what do? You put your horsepower on top, your watts on the bottom, so the watts can go away, right? So the second blank is always your units. Always put your units in place, then match the numbers. Well, here's the number. 1 horsepower is 746 watts. So divide the 9,800 by 746. And what do you say you got? 13 point what? 0.1 horsepower. Let's see what they got. They rounded to 13. Okay, they rounded to 13 horsepower. Because here's why. Even though they have 4 digits here, 3 digits here, they only had 2 digits here, and also G was only 2 digits. So yeah, that's why they rounded to 13. Don't carry around the extra decimal you can't deal with. Okay, so that was example 3.3. Let's do example 3.4. This should be something. A 150-pound person runs up a 15-foot stairway in 10.0 seconds. Okay? Now, that 15 feet is not this way, it's this way. This is your 15-foot stairway. Okay? I'm not going to do it all the way. You got the general idea. The guy down here starting to run here, okay, or it could be a gal, okay, is 150 pounds. What's that a measure of? Weight, which is a force, exactly. And this would be your distance, the distance up, not the whole distance, length of the stairwell, it's the distance up. And he does it in 10.0 seconds. What's that a measure of? Horizontal does not make any, there's no work involved with the horizontal displacement. You're absolutely right. 10 seconds measures time. So how much, what is the horsepower rating of that person? How would you get it? Okay, 150 pounds times the 15 feet, that gives you foot-pounds of, what does that measure? Foot-pound measures? Work, yeah. Pounds measure force, work, divided by 10.0 seconds. That'd be, say again? 225 what? No special unit, foot, pounds per second. Okay, but it asks for horsepower. So what are we going to multiply by? Blank, blank, trying to get the horsepower. You need the foot-pounds per second in the denominator, and you need horsepowers up here. Now, how many foot-pounds per second makes 1 horsepower? How many horsepower makes 1 foot-pound per second? 550 which way? Denominator, that's in the foot-pounds per second. 550 foot-pounds per second is 1 horsepower. So divide the 225 by 550, and what do you get? Second? No, it's not quite 0.5. If that was 275, that would be 0.5. Yeah. Okay, what is it? 0.4? Okay, we'll round that to 0.41. Because again, 2 digits. They have 3 there, but others are only 2. This could be 3 digits, but this one's only 2, so we round it to 0.41 horsepower. Not quite 0.5. Okay. All right. Let me think. 115. We went a little over, didn't we? Sorry about that. We're just having so much fun. It was supposed to be an hour and a half of class. But this is exactly where we're supposed to stop. I just talked too much. Sorry about that, guys. We'll make it up in lab, I think. What's that? How many what?
Apples
Oh, just one. Okay.
Next time
But
do
I had a
about
sandwich and salad too, huh?
Next time, just do about half an hour.
No, 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 no. All right. What I'm going to do is pause it, or I'll mention here, how the procedures won't quite be like this, but they're going to be pretty close. You'll have teams of usually 3 volunteers. We're going to have 3 teams of 3 plus 1 team of 2. Okay? Now, do any of you have any physical reason that you can't do stairs?
I'm lazy.
Okay, that's not good enough. That's mental. That's not physical. Okay? All right.
Some screws and stuff in my ankle.
You what?
I got some screws and stuff in my ankle.
Okay, so you can't go upstairs. Yeah, right.
I really do that.
Yeah. Wow. Okay. Second. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. We still got 2 more.
They don't carry them down the steps right
Say what? Yeah, I'm sure they do. They are such good classmates. I haven't seen them falling down, so I'm sure they did it. Okay. Now, I wish the others were here. We're going to do something a little different from what they say, and I wish they were here to do it. What they say here is the vertical heights of the stairs can be found by measuring the height of 1 step, then multiplying by the number of steps. Oh my word, what a pain in the neck way to do it. We're going to do it a lot simpler than that. Is that it now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We got it. So, we're short 1 meter stick, but we've got enough stopwatches. Okay? So, the meter stick we use right at the beginning, so as soon as the first team finishes with the meter stick, then I'll take the meter stick to the 4th team. So you'll need to be 3 teams of 3 and 1 team of 2. Y'all got it split up yet? You 3? You 3? Okay. There's a meter stick. You're with him, so you won't need one. There's a stopwatch and a stopwatch. Okay. And we got else? 3 and a 2. You 2 are going to be? Okay. Well, I'll hold off and give you that. You'll have that. And you can have that. And you have this. I'll get your meter stick for it. Okay. Let's go to the nearest stairwell. Okay? So bring your stopwatches and your meter sticks and your labs. Oh, I have your lab, don't I? Mason. Everybody got a lab? Okay. Get your lab, your meter stick, and your stopwatch. We'll go to the nearest stairwell. Y'all are heading the right direction, right here. Follow that guy with the, yeah, never mind. Okay. Hey. All right, good deal. Good. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 2 more coming, right?
Oh, no, that's hard.
Okay. 2 more coming? Oh, yeah, the screws in his foot. Okay. Yeah.
He's got plate.
He's got screws.
Like fine china plate. That's what he said.
I'm going to pause this. No reason to. All right. The first thing you're going to do is, well, you're going to put your own weight in, and you can be as honest or dishonest about it as you want. Okay. I'll leave that up to you. But then the vertical heights of the steps. Rather than measuring 1 step and multiplying, we're just going to do it a little bit simpler way. So what I may do is set this down here where it might be able to pick up my voice or not. And let me bum a stick here. Now notice we're using which? Everything's measured in pounds and feet. So turn your meter sticks to the guard stick side, and you're only going to go to 36 inches. That extra 3 inches or so, that's what makes a meter. So what you're going to do is start here at the floor, and everyone will do this. Huh? Yeah, okay. You'll go, that's 3 feet. Another 3 feet. Okay. Want to hold that? Thank you. Let's see. I think what we'll do, this point here, we'll translate over here, hoping they did everything pretty evenly. Okay. Another 3 feet, so you keep up with this and you keep on going. Now someone needs to get on the top. Now there's a wall here, but the floor is below the edge of the wall. So don't measure to the top of the wall, measure to estimate where the floor is.
You got a measuring tape?
I don't have one with me, okay? But besides, you can't go straight up because of the stairwells and stuff. So you're getting to the closest foot is all you need to do. So measure from the floor to the floor up there. That leads to what you're going to be doing next. I'll give you this, and you let me use your stopwatch. Okay? So, now, I'm going to model for you walking up the stairs. At whatever rate you feel is comfortable walking up the stairs, you're going to do that. One of your guys is going to be up here with the stopwatch. And as soon as you take the first step, he's going to press start. You walk up the stairs, turn, and walk up there till you get to that level. Then you'll press stop. Stop. Okay. That's going to be the time it took. You have your weight, that's the force. You have the height, that's the distance. And you have the time. Record all those on your sheets. You see the blocks for them all? Right? That's all you have to do out here. Then you set reset. Okay? Then the next time, now this is the most important thing I'm going to say with this, I think. The next time, the same person is going to run the steps. The timekeeper is still up there, but when I say run the steps, I say run the steps at a safe speed. I don't want any accident reports. That's going to put us into spring break, okay? We don't want to go there. He's got 3 hours of travel, okay? We don't want any accident reports. So go as fast as safely possible, okay? You notice the rate at which I walked up? Just do it somewhat faster than that, okay? Just somewhat faster, but no injuries. If there's injuries, I'm not going to be a happy camper.
Can we skip a step or do we go?
Huh?
Can we skip a step or do we have
I
to
don't
go?
care how you do it. You just get from there to there safely at a more rapid pace than what you want. You record those times. Okay? The timer is up here. Start. Stop. Record the time. Record the time. Okay. This is be very careful with this one. Whoever's got it, be sure you press it all the way. Okay. Now, then you change and the second person does it. And then as long as the team with only 2 people, you're done when you got those 2. The team with 3, if all 3 of you can do it with the third one, and you've got plenty of room over here in the margin that you can get all the things you need there, right, for the third person. Volunteer seat. Okay, the more people you do, if you do make some errors, they're not going to count as bad because you got more data points. Okay? Now, once you got the height measured, once you got your times measured, you recorded your weight, the height, the times, come back to the classroom. Do you prefer that classroom or the one we just came from? You want that one? 259?
Yes.
Okay, come back there. So one team, is this your stopwatch? That's mine, this, and this is your that. Right, okay. Now, I don't know if all that recorded. Okay, one team stay here, start measuring on your the height. The other 3 teams, say again?
Measure one step, however
You can if you want to, but that introduces more error. However you want to measure the height from the bottom to the top. Okay, I'll let you decide. One team stays here. Which team is this? Okay. The other three teams come with me. Okay. Two teams can stop right here if you want to, and one team continue on with me. Okay? Okay. Y'all got a stopwatch and a... Yeah, good deal. Okay, watch this. Floor is wet. Don't slide. Too bad. Okay. Okay? Here's your stairwell. Measure the floor from here to the floor up there. Be sure don't count the wall, but just the floor. Do that first, and then do the start your measurements. Okay? It's supposed to be a lift. Okay? It may be at the top. Okay. No, you won't. Okay. All right. You know, any questions? Any questions? Okay. Okay. Yeah.
Will the weight be just like constant?
Your weight. Yeah. Your weight will be the same walking and running. And B and C. All three will have different weight. That's why C, you don't need but one block here because the weight doesn't change. You'll need one height here. Here you'll need one for walking, one for running. You got one each. Here you'll need double up here. Yeah. But you can use space at the bottom too. Okay. Okay, we got two teams, right? Head that way, the way Alfred's going, that way. Both teams. Good deal. We go through the doors, we'll take a right. Okay, that's bad news, huh? You got two tests to take. Howdy. Howdy. Okay. Okay, y'all are going to keep going, but you can wait here for now. The team with the stick and the stopwatch, right? Okay. You're here. Yeah, I'll get you a stick. Okay, you measure from that floor to the floor there. Okay? You figure out how to do it. Measure from the floor to floor. Okay? Now count the wall, the floor. Yeah, that's what I would do. Okay? Okay, you ready? Come on. I'll have to go get a lab for you, but I'm going to hang you up with the team right here. You just got a third person. Carrie's here. Okay, come this way. I'll get you one when I get the stick. Y'all don't happen to have a meter stick I could use, do you?
Meter stick?
Yeah. Yardstick?
We got measuring tape.
Oh, never mind. We'll get it. All right. Well, be okay with measuring tape, I guess. Okay. This is your stairwell. Okay. As soon as I get you something to measure with, you measure from that floor to that floor. Okay. Not the wall here, top of the wall, the floor.
Just top step.
Top step. Bottom there to top step there. Okay. I'll go get you that, and I'll get you a stick too, because they're probably through with the first one. Okay, number 2 on the questions. Okay, after you've done the data, then number 2 on the questions. There's 5 questions on page 126 and 127. Number 2 at the top of 127. Is there some limit to the height of the flight of the stairs used and the horsepower developed? What you think? Okay, so if you were running the stairs at Bryant-Denny Stadium, you could probably do it as much horsepower as you did here. Why not?
I didn't run very fast on mine, so I'm not doing that.
You might be able to, huh? What's that? Okay, yeah. If you're going at the same rate, yes, but I bet you, I know when I was digging in the backyard, I could start that day probably pretty close to half a horsepower. By the end of the day, if I was doing a quarter of a horsepower, I'd be lucky, okay? I just couldn't sustain it. So that's what I interpret that to mean. I don't know if that's what they meant. Like I said, to me, some of these questions are a little shaky.
So it would be no because eventually your energy will
Yeah, that sounds good to me. If you got a better answer, you can put it down. Any other questions? Okay. For those who still need to work on calculation, I know one team just got back. Please get your calculations done too. Okay. I'll take up the meter sticks.
Number 3 don't make any sense either.
What's that?
Number 3.
Okay, let me check number 3. Oh yeah, that's a good thought question, isn't it? We're still recording. Could the horsepower developed by a slower moving student ever be greater than the horsepower developed by a faster moving student? When? How?
If he's greater in mass.
Yes, if he weighed significantly more. Okay? Absolutely. Might be a little bit slower, but weigh a lot more. So now his line number 1, weight is much bigger. Vertical steps is the same. Time may be a little less, but the work done, force times displacement, much larger. If the time wasn't much less, then his power may be greater. You're absolutely right. Make sense? Any others? Have them ask me. Okay, need 3 of these little stopwatches. Should I get that? Thank you. Yep. Appreciate it. Yeah. What's that? Okay. Okay. These you fill in today. I know y'all didn't have as much time, but I'm pretty sure that you were up to 9 feet when you said it was on that line right there. Oh, you were doing that? Then you went one more. You just pick up, didn't you?
I mean, because you see it from the top of the floor.
Okay, you do the bottom of the floor?
You see it from the bottom of the floor to the top step.
Okay.
To the top step.
All right.
Probably the same.
Okay, maybe that part was the building. It's okay, it'll still work. Okay. So anyway, this is what we do. Work is force times distance. This number. This plus this times the same number. That's what we fill in there. Right. Then power, once you figure out what the work is, take the work divided by the time. Work divided by the time. Work divided by time. Divided by time here and divided by time there. Okay? And then that's your power. Once you figure out what this one is, divide this number by 550 and then put it together. Okay? Alright. I got one more little bitty stopwatch somewhere. Ah, no, that's there. Ah, you got it. Okay, trying to replace his clock with it. I think he liked mine better. I could tell. Huh? Okay. All right. Oh, that's your. Oh, okay. Okay. I want to say you did 2 today. I've got to find my roll book. Where it is. Okay. Good deal. Thank you. You ready or not? It doesn't matter.
I had a question.
Okay.
I don't have a calculator today with me. I couldn't find the one I had from that.
Okay. I've got 2 in my office. I can run and get 1 from there. Okay. Okay. Any more? That's all I got. Okay. But if you need one, some phones have calculators on them.
Yeah.
You can use those if you want to.
I can use that then. I just didn't know if you.
Yeah, that's all.
Okay, you just can't call your girlfriend to give her the answer, okay?
I don't have a girlfriend, but
Yeah, I
doubt you.
I
I'm just gonna give you the right answer.
I know some people don't like you to have phones out.
Yeah.
I really don't care. You know, if you're just doing calculations on it, just calculate. Okay. I would take it some of you are ready for your test then or not? Okay. Yeah, well, if you want to. You okay with it? That's what I meant to ask you when I was asking before. All right, good deal. Thank you. Okay, you can have your formula and equation sheet if you got it. You ready for it? Let me know. Okay. Is that okay? Good deal. Thank you. Okay. Deal. And by the way, while I've got the recorder on, this would be a great time to work on your papers. You've got a whole week, no classes. Great time to work on your papers. Wouldn't it be? Huh?
I can't remember how long you said this.
1 to 2 pages.
1 to 2 pages.
Double space.
About
Standard font.
about 1.5 pages.
Yeah. It's got to be greater than 1. You can go over 2 if you want to. I don't take off for being too long, but I do take off for being too short. Okay? Okay? I'm not rushing. No. For those with the test, lab time is over. We don't work in groups anymore. Okay. Okay. Ready for yours? This is test 1, chapter 1. All right. Unless there's more questions, I'm going to shut down